All right, here's example 5, which is a great example for something engineers might need to do to make sure that things are stable, built correctly, and not going to fall under pressure. The rope that's used can handle the tension on it, that things are going to be safe in an earthquake. There's all sorts of things that engineers have to consider when they are designing and figuring out how things should be built. So here we go. First of all, I'm going to use 50 pounds instead of 12 in my example, so change that number in your notes. A 50-pound speaker is suspended from the ceiling by 2 support braces. If one makes a 60-degree angle with the ceiling and the other a 30-degree angle with the ceiling, what are the tensions on each of the supports? So we need to make sure whatever hardware we're using to fasten the supports and whatever the supports are made out of, that it's going to be able to handle, that it's rated for the tension that it's going to have to handle for that speaker in a venue where you want the speaker hanging from the ceiling so that everyone can hear what's going on. So we're going to call this support T2, vector T2, and we're going to call this support vector T1. So if this is 60 degrees to the ceiling, then that would also be 60 degrees from the x-axis. If we do a little like XY graph right here in the middle. And if this is 30 degrees to the ceiling, then this would be, I keep meaning for that to be a black line, then this would be 150 degrees to that support from the x-axis. So those are the angles we're using in our component forms. So to find the component forms, we need the magnitudes and the angles. We know the angles, we don't know the magnitudes. That's what we're trying to find. Since we're trying to find the magnitudes, and this notation with the double lines is rather clunky, and since magnitudes are just scalars anyway, I'm just going to use variable t1 to represent the magnitude of vector t1 and t2 to represent the magnitude of vector t2. Don't forget we have the vector for the weight of the speaker as well. We're going to call that vector w, and its component form is 0, negative 50. Because of the 50 pounds, it's going this direction because gravity pulls it down. All right, altogether, we want this system to have equilibrium. We want everything to be balanced, and that means we want the total weight and tension to equal out to 0. So with that in mind, we want T1 plus T2 plus W. We want these 3 vectors to end up with a resultant of 0. Okay, let's go ahead and start putting these together with the information we do know. So our first vector would be T1. We don't know what that number is, but we know it's going to be T1 times the cosine of 60, and the cosine of 60 is 1/2. And then the other part of our component is going to be T1 times the sine of 60, which is square root of 3 over 2. So there's our first vector. And we're going to add that to vector T2. So T2 would be magnitude T2 times the cosine of 150. That's going to be negative square root of 3 over 2. Because it's second quadrant angle, cosine is negative. And then it'll be T2 times the sine of 150, which sine is positive and it's a 30-degree reference angle, so it would be 1/2. Okay. Then if we add that to our weight vector, 0, negative 50, we call it negative, of course, because if our xy axis is here, it's going downward. Our vertical distance magnitude is 50. And together we want that to result in 0. So a 0 vector, which basically would mean our components are 0, if you want to write it that way. Okay, So we have our x components, we have our y components. That allows us to write two different equations. So we're going to have two equations and two unknowns that we can solve as a system. So right here we will have t1 times 1/2. I'm just going to call that t1 over 2. We're going to add that to t2 times negative square root of 3. We're going to call that negative square root of 3. Actually, I'm going to do negative t2 square root of 3 over 2. And we're going to add that to 0. So those are the x components of all three vectors, and we want that to reach equilibrium, which is 0. Now let's look at the y components. So that will be square root of t1 times the square root of 3 over 2 plus t2 times 1/2, so t2 over 2, plus our negative 50 equals 0. So now there are no more vectors in our problems. We simply have everything as scalars because we're just talking about the x and y components. So we don't have to worry about these being vectors. We just solve them like we normally would. Okay, first of all, I don't like the fractions. So we can get rid of the fractions in everything by multiplying everything by 2. And that's going to allow our fractions to cancel, which is fabulous. And of course the 2's will cancel for the fractions, and 2 times 0 is just 0. So we end up with, just showing that that's going away. Maybe I just want to, I don't know, you guys know what's happening. So that leaves us with t1 minus t2 square root of 3 equals 0. There's one of our equations. Our other equation is the 2 cancels out here, so we have t1 square root of 3 plus the 2's cancel, so t2. Now here there is no fraction canceling the 2, so we have to actually multiply the 2 by 100. So instead of calling that adding negative 100, I'm just going to write minus 100 equals 0. Okay, I'm going to go ahead and move the 100 to the other side. So here's system of equations number 1. So I'm going to call this equation number 1. And we're going to call this one equation number 2. Okay, so to solve this, we want to solve this. We could use elimination, we could use substitution, we could use a matrix. There's all sorts of different ways to do this with a matrix. I think substitution is our best bet because this one right here equal to 0. We can just move that to the other side. And then we can take this and substitute it into here, right? I went too far. So substitute it right there. All right, so I'm going to say that T1 is T2 square root 3. So I'm substituting that in times square root 3. And then we're adding T2 to that, and together those add up to 100. So square root of 3 times square root of 3 is 3. So we have 3t2 plus 1t2 is 4t2, which equals 100. And that means that tension number 2 is 25, and these tensions are given in pounds as a type of force measurement. So if you look at things at the hardware store and they're rated to hold things up, they'll tell you, like if you buy hooks to hang on the wall, how many pounds they will hold up. Okay, now that we know T2, we want to go back and put that back in here to find T1. So T1 is going to be T2, which is 25, times the square root of 2. Now that would have an approximate answer of like, I don't know, someone calculated it, but now I don't remember what it was. 43 maybe? I don't remember what it was. But anyway, we're going to give the exact answer. So here are the tensions on those supports, and we need to make sure as an engineer that we are instructing our construction people to use correct materials to hold those tensions so that everything will stay in place and not fall on people's heads.